Hi everyone, welcome back to my Aquarium Chemistry YouTube channel. In this video, we'll see about resonance effect and its applications. Before that, let us start with resonance. We will see what is resonance means. Okay? Okay. We know that bond length is inversely proportional to bond energy. If you write the order of bond length of alkyne, alkene and alkane, the bond length order will be alkyne is less than, alkene is less than alkene. If you write the bond energy order, the bond energy order exactly reverse to that of bond length order. That is, alkyne will be having greater bond energy than alkene. Alkene will be having the greater bond energy than alkane. Okay, this is the known data. Okay, so let us take an example, that is nitromethane, that is CH3NO2. If you write the structure of nitromethane, CH3 bonded to nitrogen, N double bond O and N single bond O. Here, the nitrogen will be having a positive charge because of 4 bonded pairs. So, if you write the bond energy order for this molecule, consider, okay, N double bond O, bond energy is X, and the bond energy of N single bond O is Y. If you write the bond energy order, okay, what will be that? According to this, according to the known data, it will be X is greater than Y. X greater than Y. Right? This is the bond energy according to the known data. But experimentally, it will be X is equal to Y. Okay? X is equal to Y. Therefore, this structure fails to explain all the properties of the molecule. Right? Yes. When single Lewis structure, when single Lewis structure, when single Lewis structure fails to explain all the properties of the molecule, all the properties of the molecule, okay, then we need one more structure, right? Then we need one more structure, okay? Yes, we need one more structure. Another structure can be written by using double-edged arrow. Okay, what happens in this case? We will see. Here, these pi electrons shift here. Okay. Okay. Then what will be the structure? That is CH3 bonded to nitrogen, N single bond O, and here N double bond O, because the pi electrons are shifted to this oxygen, right? Yes. As usual, positive charge will be on nitrogen, negative charge shift to oxygen. Okay. Yes. Again, in this case also, you're not going to get the experimental bond energy, that is X is equal to Y, right? Okay. Consider this is a structure 1 and this is structure number 2. Okay. These 1 and 2 structures are, called resonance structures. Resonance structure. Okay. Okay. So again, in the second structure also, we are not going to have the experimental bond energy, that is X is equal to Y. So I will write one more structure, that is CH3 N single bond O and single bond O. So here in the third case, These pi electrons are distributed to both the oxygen, leads to the formation of partial double bond. Partial double bond. Again, nitrogen will be having the positive charge and one negative charge is distributed over two oxygens. Okay, that is minus half and minus half. Now, if you write the bond energy order, that is, consider this is X and this one is Y. If you write the bond energy order, definitely it will be X is equal to Y. Okay, X is equal to Y. Again, this is the experimental data. Okay, experimental data. So, this structure is real, right? This structure is a real structure and which is called as resonance hybrid. Okay, resonance hybrid. Okay, so we can say that resonance structures are hypothetical. Resonance structures are hypothetical. That means they are imaginary. But the resonance hybrid, okay, resonance hybrid is a real structure. Resonance hybrid is a real structure. Okay. So now we will define what is resonance. Okay. Here the resonance means the phenomenon of existence of two or more structures for a molecule or ion for a molecule or ion differing only in the distribution of electrons, but not in the relative position of the atoms, but not in the relative position of the atoms, right? In all three cases, if you see the position of the atoms, okay, if you see the position of the atoms, there is no change in the position of the atoms. Am I right? There is no change in the position of the atoms. The only change is the distribution of electrons. See, here the pi bond is here in the first case. In the second case, pi bond is here. In the third case, the pi electrons are distributed to both the oxygens. That means there is only difference in the distribution of electrons, but not in the relative position of the atoms. Okay, this is nothing but resonance. The resonance means the phenomenon of existence of two or more structures for a molecule or ion differing only in the distribution of electrons but not in the relative position of the atoms. Okay. Okay. Let us see conditions for resonance. Conditions for resonance. First one is molecule should be planar. Molecule should be planar. That means all the atoms in the molecule should be in same plane. And second one is there should be a conjugated system. Conjugated system. Here the conjugation means overlapping of p orbitals of two adjacent atoms. Okay. For example, NH2 single bond CH double bond CH2. Here this is pi bond and this is the sigma bond and here nitrogen will be having a lone pair of electrons. This can also be written as, okay, NH2 single bond CH, single bond CH2, okay. The pi bond can be represented as overlapping of p orbitals, right? These two p orbitals are overlapped, and this is pi bond, okay. Here nitrogen also having the lone pair of electrons, that is like this, okay. So electrons move easily. Electrons move easily when the p orbitals are in parallel position. When p orbitals are in parallel position, okay. Here all these p orbitals are parallel position so that the electrons can move easily. Here this lone pair of electrons can easily move here, and this pi electron can shift here, okay. That can be written as NH2 double bond CH, okay, CH single bond CH2, okay, CH2. Here since nitrogen has 4 bonded pairs, it will be having positive charge, and here the pi electron is shifted towards the carbon atom so that the carbon will be having the negative charge, okay. This is the one more structure, and these two structures are, these 1 and 2 structures are resonance structures, right? NH2 single bond CH, single bond CH2. We will write the p orbitals. Nitrogen having the p orbital, the overlapping of p orbital. Yes, this is the overlapping of these two p orbitals giving pi bond, and the negative charge present on the carbon will be indicated like this, okay. Yes. So here the electron can easily move when the p orbital are in parallel position, okay. Here these two structures, structure number 1 and structure number 2, are resonance structures. We will move on to types of conjugation. Types of conjugation. First one is pi bond conjugation. Pi bond conjugation, that is presence of alternate single and double bond. For example, CH2 double bond, CH single bond, CH double bond O. So in this case, these pi electrons moves here and this pi electron shifted to oxygen. That can be written as CH2 single bond CH double bond CH single bond O. So here the electrons are moving away from this carbon atom so that this carbon atom will be having positive charge, and here these pi electrons are moving towards oxygen so that oxygen will be having negative charge. These two structures are called resonance structures, and these resonance structures are also called as canonical structures. Canonical structures, which can also called as contributing structures. Contributing structures. Okay. Next type of conjugation is lone pair pi bond conjugation. Lone pair pi bond conjugation. For example, NH2 single bond CH double bond CH2. Here the nitrogen will be having lone pair of electron. These lone pair of electron moves here and this pi electron shifted to carbon, which can be written as NH2 double bond CH single bond CH2 minus. Nitrogen will be having positive charge because of 4 bonded pairs. Next type is negative charge pi bond conjugation. Negative charge pi bond conjugation. For example, CH2 minus single bond CH double bond CH2. This negative charge indicates the presence of a pair of electron or presence of 2 electrons. Okay, this will be shifted to here and this electron is shifted to carbon atom. So that CH2 double bond CH single bond CH2 minus, because here pi electrons are shifting towards carbon atom, so that the carbon will be having negative charge. Fourth type of conjugation, that is pi bond and vacant orbital conjugation. Pi bond vacant orbital conjugation. For example, H2b single bond CH double bond CH2. Here the boron will be having vacant orbital. Now this pi electron shifts here. Okay. Therefore, H2b double bond CH single bond CH2 plus. Okay. Next type of conjugation is pi bond positive charge conjugation. Pi bond positive charge conjugation. For example, CH2 plus single bond CH double bond CH2. So here again this pi electron moves here, so that CH2 double bond CH single bond CH2 plus. Okay. Next type of conjugation is lone pair vacant orbital conjugation. That is lone pair vacant orbital conjugation. That means it will be having positive charge. Okay. Or vacant orbital. For example, NH2 single bond CH2 plus. Okay, what happens? Nitrogen will be having lone pair of electron. This lone pair of electron is shifted here, so that which can be written as NH2 double bond CH2. Here nitrogen will be having positive charge because of the 4 bonded pairs. Okay, these lone pair of electron are shifting to the vacant orbital of carbon. Okay, next type of conjugation is pi bond free radical conjugation. Pi bond free radical conjugation. For example, CH2 free radical single bond CH double bond CH2. Here this pi bond undergoes homolytic fission. Okay, so therefore this free electron, this single electron combined with the electron which is produced from the homolytic fission and gives this structure, that is CH2 double bond CH single bond CH2 free radical. This is all about types of conjugation. We will see some important points of resonance structure, that is, first one is, it is hypothetical concept. It is hypothetical concept. The next one is, resonance is intramolecular process. Intramolecular process. Okay. Next one is, resonance structures are imaginary. resonance structures are imaginary, whereas resonance hybrid is real. Next one is atom cannot move in resonance. Atom cannot move in resonance. Okay. Next one is total number of electrons. Total number of electrons remain same. Next point is any structure violating fundamental rule or octet rule. Any structure violating fundamental rule or octet rule is not accepted as resonance structure. For example, carbon always will be having 4 bonds, right? Writing 5 bonds to carbon is the violation of octet rule or a fundamental rule. Those type of structures will not be accepted as resonance structures. This is about some important points of resonance. We will move on to stability of resonance structures. In that, first one is extended conjugation and cross conjugation. So here extended conjugation means presence of alternate single and double bond. That is, okay, double bond, single bond, double bond, single bond and double bond. Here the conjugation is taking place in a linear manner. This is extended conjugation. Coming to cross conjugation, that is double bond, single bond, double bond, single bond, double bond, double bond, single bond, double bond, single bond, double bond. Here the conjugation is possible in this way. The conjugation also possible in this way and also in this way. This is cross conjugation. Okay. Okay. Coming to stability of resonance structures, extended conjugation is more stable than cross conjugation. Extended conjugation is more stable than cross conjugation. Okay. Okay. We'll take an example. So in this case, the conjugation is taking place in this direction. That means in a linear manner. We'll take one more example. So in this case, the lone pair on the nitrogen may involve in conjugation with this pi electron, also involve conjugation with this pi electron. So coming to stability of these two, the first one is more stable than second one, okay, because of the extended conjugation. Okay, let us move on to next one. Coming to next case, that is stability is directly proportional to number of benzenoid rings. With increase in the benzenoid rings, stability increases. Consider benzene, naphthalene and anthracene. Okay. The order of stability is more the number of benzenoid rings, more will be the resonance structure and more will be the stability. Therefore, benzene is less stable than naphthalene, is less stable than anthracene. Okay, this is the more stable benzenoid ring. Coming to next one, that is two separating benzenoid rings are more stable than fused rings. That is, separating benzenoid rings are more stable than fused rings. For example, This is separating benzenoid rings. These two benzene rings are separated by carbon-carbon single bond. So these separating benzenoid rings are more stable than fused rings. That is, for example, naphthalene. Okay, here both the benzene rings are fused. In this case, benzene rings are separated. Okay, therefore, these two separated benzenoid rings are more stable than fused benzenoid rings. Coming to equivalence resonance, potential energy of all the resonance structures are same. Okay, the potential energy of all the resonance structures are same, and also contribution of all the resonance structures are same. Contribution of all the resonance structures are same. Okay, we will take example, that is, okay. So if you write the resonance structure, this pi electron moves here and this comes here. Okay, therefore it can be written as, here the pi bond, positive charge shifts here. Okay, again if you write the resonance structure, this pi bond comes here and this pi electrons moves here. Therefore you can write it as positive charge will be on here. So in all cases, positive charge is on carbon atom. Okay, so all in three cases, this is first one, second and third. In all three cases, the potential energy of all the resonance structures are same, and also the contribution of all the resonance structures are same. Okay, these are nothing but equivalence resonance structure. If you consider one more example, O minus, okay, and one more, if you write the resonance structure for this, negative charge comes here and this pi electron moves here. Therefore, the structure is double bond O, here double bond, here negative charge. So in this case, the negative charge present on oxygen and here the negative charge is present on carbon atom. Therefore, these two structures are non-equivalent. Okay. Stability among these two is, if you consider this is A and this one is B. Okay. So here in both the cases, 3 pi bonds, here also 3 pi bonds. But in first case, negative charge present on the electronegative atom is more stable. Therefore, A is more stable than B. This is the stability order.
Again, in stability of resonance structures, we have another set of rules. We'll go to that, okay? The first one is neutral species, okay, or neutral resonance structures are always stable than charged resonance structures. Okay, neutral resonance structures are always stable than charged resonance structures. Consider an example, that is CH2 double bond, CH single bond, CH double bond O. In this case, these pi electrons are involved in delocalization, right? Yes. So we can write one more structure, that is CH2 single bond, CH double bond, CH single bond O minus, here C plus. Okay, this is 1 and 2. So among these 1 and 2, which is the more stable resonance structure means, here this is the neutral resonance structure which has no charge. This is charged resonance structure. Always neutral structure. Neutral resonance structure is more stable than charged resonance structure. Therefore, 1 is more stable than 2. Okay. Coming to second one, that is more the number of pi bonds, more will be the stability. That means number of pi bonds is directly proportional to stability of resonance structure. Stability of resonance structure. Okay, we'll take an example. HC double bond O OH. Okay, and another one is HC single bond O minus, here C plus OH. Okay, this is 1 and 2. Okay, in these two cases, which is the more stable resonance structure? Here, how many pi bonds are there? In the first case, 1 pi bond. In the second case, we have 0 pi bond. More the number of pi bonds, more will be the stability of the resonance structure. Therefore, 1 is more stable than 2. Coming to third one, in that we have stability of anion increases. Stability of anion increases from left to right in the periodic table. That is, negative charge on carbon is less stable than N minus, is less stable than O minus, is less stable than F minus. Okay. Here, the negative charge on the more electronegative atom is more stable. Okay, negative charge on more electronegative atom is more stable. Okay. Next thing is stability of anion. Okay, stability of anion increases from top to bottom in the periodic table. Okay, that is, F minus is less stable than Cl minus, is less stable than Br minus, is less stable than I minus. Okay, in this case, I minus is more stable because of its more size. Okay, stability of anion increases from top to bottom because of increase in the size down the group. Okay, priority should be given to the negative charge on the more electronegative atom. Okay, if you write the priority order, negative charge takes the preference over the positive charge. Okay, this is the priority order. We'll take an example, that is HC double bond OH, HC single bond O minus, C plus OH, H single bond C, single bond O plus, C minus, and OH. Okay, this is A, B, C. Among these three, which is the most stable resonance structure? We know that first we have discussed, the first rule is neutral species are more stable than charged resonance species. Okay, now therefore A is more stable because it is neutral. Okay, after that, coming to second rule, how many pi bonds are there in B and C? There is no pi bonds. According to second rule, we cannot decide the stability. Coming to third rule, here the negative charge on the electronegative atom is more stable. Okay, here the positive charge on the oxygen atom, that is electronegative atom, is less stable. Therefore, B is more stable than C. This is the stability order. More the distance between positive and negative charge. Okay, more the distance between positive and negative charge, lesser the stability of resonance structures. Okay, if the distance between the positive and negative charge is more, then the stability of the resonance structure is less. Okay, we'll take example, that is here double bond, here double bond, double bond. Okay, next one is single bond O minus, positive charge on carbon atom, there double bond, double bond. Next one is single bond O minus, here double bond, here double bond, here positive charge. First, second, and third. Which is the most stable resonance structure among these three? According to first rule, neutral species are more stable than charged species. Therefore, the stability of the first is greater than these two. Okay. Next, coming to second rule, here we have 2 pi bonds. Here also we have 2 pi bonds. Based on this, you cannot decide the stability of the resonance structure. Coming to third rule, that is negative charge present on the electronegative atom. Negative charge present on the more electronegative atom is more stable. So here in both the cases, negative charge is on oxygen. So we cannot decide the stability according to third rule. Next, coming to fourth rule, the distance between the negative and positive charge increases, which decreases the stability of resonance structure. In the second case, the distance between the negative charge and positive charge is less, and in third case, distance between negative charge and the positive charge is more. With increase in the distance between negative and positive charge, stability decreases, right? Therefore, the stability of a second is greater than third. This is the stability order of the resonance structures. Okay, we'll go to a next rule, that is fifth rule. Like charges and adjacent positions are least stable. Okay, like charges on adjacent positions are least stable, or least stable. That means presence of positive next to positive charge, or negative charge next to negative charge, or a lone pair of electron next to negative charge. Okay, these are the like charges present on adjacent positions are least stable. We'll take an example. NH2 double bond, double bond. Again, NH2, here double bond, negative charge, here positive charge. Coming to next one, NH2, here negative charge, here positive charge, and here double bond. Okay, so first, second, and third. Which is the most stable? According to the first rule, charged species are less stable. So that this is the neutral species, therefore one is more stable. Okay. Next, coming to 2 and 3. Here also there is 1 pi bond, here also 1 pi bond. You cannot decide based on that. Next rule is third rule. Here also the negative charge present on the carbon atom, here also the negative charge present on the carbon atom. know, we cannot decide on that. Next, fourth rule is the distance between the positive and negative charges. In both the cases, the distance between the positive and negative charge is same. Coming to fifth rule. Fifth rule says that like charges and adjacent positions are least stable. Okay, you see negative charge, positive charge, and then lone pair. Okay, here positive charge, negative charge, and lone pair. So here the negative charge and the lone pair are at adjacent positions. Okay, therefore third one is least stable. Okay, second one is most stable. This is the stability order. You have to go according to the set of rules given so that you can solve questions easily.
Okay, now we will move to resonance effect. Resonance effect, which is also called as mesomeric effect. Mesomeric effect. Okay, first we will take example, that is, consider phenol, single bond OH. This is the phenol. Here oxygen has a lone pair of electron. Okay, this lone pair of electron of oxygen involved in the conjugation. That means this lone pair of electron comes here and this pi electron shifted to here. So that you can write the resonance structure. Here double bond OH, negative charge, here double bond and double bond. Oxygen will be having the positive charge. Okay. Here again this negative charge involved in the resonance. Okay. So that we can write here double bond OH, double bond here, negative charge and double bond. Okay. Next, again this negative charge involved in the resonance. Yes, that can be written as here double bond, double bond, double bond OH, positive charge, here the negative charge. Again this negative charge involved in the resonance, and this pi electrons will be taken back by the oxygen. Okay. So that double bond, double bond, double bond, here single bond OH. Okay. This is the resonance structure of phenol. Okay. Here the interaction between lone pair and the pi bond is taking place, which is creating the polarity in the molecule. Okay. Here the interaction between the lone pair and the pi bond produced polarity in the molecule. Okay, produced polarity in the molecule, which is continued through the chain. Okay, we will take one more example, that is CH2 double bond CH, single bond CH double bond oxygen. Okay, here these pi electrons are involved in conjugation. Okay, yes, these pi electrons will be taken by oxygen. So what happens is CH2 single bond CH double bond CH single bond O minus, and here positive charge. Okay, so here the interaction between pi bond and pi bond is taking place. The interaction between the pi bond and pi bond producing the polarity in the molecule. Okay, producing the polarity in the molecule. Okay, now we will define what is resonance effect means, or which is also called as mesomeric effect. It is defined as, okay, the polarity produced in the molecule, the polarity produced in the molecule by the interaction of two pi bonds 2 pi bonds or between pi bond and lone pair of electrons. Between pi bond and lone pair of electrons present on the adjacent atom. Okay, present on the adjacent atom. Adjacent atom. This effect continued or this effect transmitted throughout the chain. The effect is transmitted through the chain. This is nothing but resonance effect or mesomeric effect. We will see some important points of resonance effect. That is, resonance effect or mesomeric effect is permanent effect. Permanent effect. Here, this resonance effect or mesomeric effect operate to pi bond. Operate to pi bond. Inductive effect is distance dependent, but the resonance effect or mesomeric effect is distance independent. Distance independent. Okay. And next one is, in inductive effect, partial charge is developed. In resonance effect, actual charge is developed. Actual charge is developed. Okay. These are all some important points of resonance effect. And in resonance effect, we have two different types and we will see what are those. First one is positive mesomeric effect or positive resonance effect. And next one is negative mesomeric effect or negative resonance effect. Okay. Okay. Coming to positive mesomeric effect or positive resonance effect. In this case, if an atom or a group, if an atom or group donate electrons to the conjugated system. If an atom or a group donate electrons to the conjugated system. Conjugated system, that is maybe a double bond or a benzene ring. Okay. Okay. We will take an example. Take a benzene ring to which NH2 is attached. So what happens here? Nitrogen has a lone pair of electrons. Yes, these lone pair of electrons involved in the resonance. Lone pair of electron comes here and this pi bond shifted to here. So that you can write the resonance structure, that is double bond NH2 plus and here minus double bond and double bond. Okay. Here the interaction between the lone pair and the pi bond is taking place, which is producing the polarity in the molecule. Okay. This is nothing but positive mesomeric effect or positive resonance effect. We'll take one more example. CH2 double bond CH single bond NH2. Here nitrogen will be having lone pair of electron and this lone pair of electron involved in the resonance. Okay. So that you can write it as CH2 minus single bond CH double bond NH2. Nitrogen will be having positive charge. Here the interaction between lone pair and the pi bond is taking place, which is producing the polarity in the molecule. Okay. We'll take a few more examples. That is, OH is an example for positive mesomeric effect. OCH3. Okay. And NR2 O C double bond OCH3. These are all few examples. So in positive mesomeric effect, what actually happening is the interaction between, in positive mesomeric effect, the interaction between lone pair and pi bond is taking place. Okay, this is nothing but positive mesomeric effect. If we move to negative mesomeric effect, if an atom or a group, consider if an atom or group which withdraw electrons from the conjugated system, okay, this is nothing but negative mesomeric effect. For example, consider benzene to which NO2 group is attached, N double bond O and O. The pi electrons of the benzene ring will move towards nitrogen. Okay, it can be written as here double bond nitrogen single bond O and single bond O. Here the positive charge, again double bond. Okay, here negative charge. Okay, this is an example for negative mesomeric effect. And we will take one more example, that is CH2 double bond, CH single bond, CH double bond, oxygen. So again here the interaction between pi bond and pi bond is taking place. Here also the interaction between pi bond and pi bond is taking place. Here this pi electron involved in the resonance, yes, that can be written as CH2 single bond CH double bond CH single bond O minus, here positive charge on the carbon atom. Okay, we will take a few more examples. Okay, NO group is an electron withdrawing group, and again C double bond O OCH3, and then C double bond O C single bond H, C double bond O CH3, okay, and C double bond O OH, okay, then CH double bond NH. These are all the examples for negative mesomeric effect. In negative mesomeric effect, the interaction between pi bond and pi bond is taking place. Interaction between pi bond and pi bond is taking place. In positive mesomeric effect, the interaction between the lone pair and pi bond can be seen. In negative mesomeric effect, the interaction between two pi bonds can be seen. Comparison of positive mesomeric groups. Okay. So first one is positive mesomeric power is directly proportional to extent of overlapping. Okay. So for example, consider CH2 double bond CH single bond NH2. Okay. So here this can also be written as CH2 single bond CH single bond NH2. Okay. Here the p orbital of the carbon atoms are overlapped to form pi bond. Okay. And here nitrogen will be having lone pair of electrons. Okay, this is the lone pair of nitrogen. The lone pair on the nitrogen involved in the resonance. Therefore, this pi electron is shifted to carbon atom. Okay, which can be written as CH2 minus single bond CH double bond NH2. Positive charge will be on nitrogen. So this can also be written as CH2 minus, okay, single bond CH single bond NH2. Okay, again the p orbitals of carbon and nitrogen will overlap to form pi bond. Okay, so here more the size of the orbitals are comparable, more will be the extent of overlapping. That is, more the size of orbital is comparable, more the size of the orbital is comparable, more will be the extent of overlapping, more will be the extent of overlapping, and more will be the resonance, more will be the resonance, which increases the positive mesomeric effect, which increases positive mesomeric power. Okay, yes. So if we take example in particular, consider if carbon is bonded with NH2 and carbon is bonded with OH and then carbon is bonded with fluorine. Okay, the question is, what is the order of positive mesomeric power? So in order to answer that question, write down the order of size. That is, carbon is greater than nitrogen is greater than oxygen is greater than fluorine. This is the order of size. Okay. So here the size of carbon and nitrogen is comparable, then size of carbon and oxygen, and then size of carbon and fluorine. Okay. So since the size of the orbitals of carbon and nitrogen are comparable, so the positive mesomeric power is greater for the carbon and nitrogen bond. Okay, then comes carbon and oxygen, and then comes carbon and fluorine. Okay, this is the order of positive mesomeric power. And we will see what is the positive mesomeric power in halogens. Positive mesomeric power of halogens. Okay, that is, fluorine is greater than, chlorine is greater than, bromine is greater than iodine. This is because due to the increase in size down the group, overlapping decreases. Okay, overlapping decreases, which decrease positive mesomeric power. Okay, consider fluorine, chlorine, bromine, and iodine. Here, the size of fluorine and carbon is comparable. Here, the size of fluorine and carbon is comparable than size of chlorine and carbon, then size of bromine and carbon, and then size of iodine and carbon. Down the group, size increases, overlapping decreases, which decreases the positive mesomeric power. Consider NH3 and NH2C double bond O CH3. Okay. Here, the question is to compare the positive mesomeric power among these two. Here, the nitrogen has lone pair of electrons, and here also nitrogen has lone pair of electrons. Here, lone pair of electron not involved in any conjugation, but here this lone pair of electron involved in conjugation. Okay. Therefore, in this case, availability of lone pair is less. More the availability of lone pair, more will be the positive mesomeric power. Positive mesomeric power. Okay. So among these two, NH3 has more positive mesomeric power and compared to NH2C double bond O CH3. Next example, consider OH and O single bond C double bond O CH3. Here, oxygen has a lone pair of electrons and here also oxygen has lone pair of electrons. Here, this lone pair of electron of oxygen involved in the conjugation so that availability of this particular lone pair decreases. Therefore, OH is a good positive mesomeric group compared to OC double bond CH3. Consider one more example, that is O minus and OH. So here oxygen has a lone pair of electron, along with that oxygen has negative charge. Coming to here, oxygen has only lone pair of electron. Here this negative charge indicates the electron density. Okay. More the electron density, more the electron density, more the electron density, more will be the positive mesomeric power. Okay. Therefore, these electrons are available easily. Therefore, O minus is good positive mesomeric group compared to OH. And next example is NH minus and NH2. Here, nitrogen has negative charge. Along with that, it has lone pair of electrons. Here, nitrogen has only lone pair of electrons. Okay. The electron density of NH minus is greater than NH2. Therefore, NH minus acts as good positive mesomeric group. To compare the power of negative mesomeric group, power of negative mesomeric group. Okay. This is decided based on the electron withdrawing capacity. This is decided based on electron withdrawing capacity. Okay. For example, NO2 is good electron withdrawing group compared to Cn minus, and Cn minus is good electron withdrawing group compared to C double bond OH. This is usually same as in negative inductive effect. Let us study about some important points of mesomeric effect. That is, mesomeric effect does not operate to metaposition. Mesomeric effect does not operate to metaposition. We will see by taking an example, that is, consider phenol. Okay, this is phenol. The lone pair on oxygen involved with the resonance. Okay, so that we can write here negative charge, here double bond OH, oxygen will be having positive charge, here double bond and here double bond. Again this negative charge involved with the resonance, so that we can write it as here double bond OH, positive charge on oxygen, here the negative charge, here double bond. Again this negative charge involved with the resonance. Okay, that can be written as here double bond OH, positive charge on oxygen, here double bond, and here negative charge. Again, this negative charge involved in the resonance. So we can write as, okay, here double bond, double bond, double bond, single bond OH. These are the resonance structures of phenol. Okay. If you see at meta position, this is the meta position, right? No charge is operated on meta position. No charge is operated on meta position. Therefore, mesomeric effect doesn't operate to meta position. Okay. Next, we will discuss about ortho effect. Ortho effect. Okay. Here, acidic strength of ortho substituted benzoic acid. Acidic strength of ortho substituted benzoic acid increases the stability. Increases the stability. Okay. Let us take an example. That is, okay, double bond, double bond, double bond, and here C double bond O, OH. This is benzoic acid. After donating the proton, it becomes C double bond O, O minus plus H plus. Okay. So in this case, here the negative charge on this oxygen will be in resonance with C double bond O. Okay. And at the same time, the resonance between the pi electrons of benzene ring and also C double bond O is also possible. Okay. The resonance is possible in both ways. Therefore, this is less stable. Less stable. We will see what if bulky group present at ortho position. Again, benzoic acid, C double bond O, OH. At ortho position, bulky group G is present. After donating the proton, it becomes C double bond O, O minus plus H plus, and at ortho position, bulky group G is present. Here, due to the presence of bulky group at ortho position, this bulky group causes repulsion. Due to the repulsion, the plane of C double bond O, O minus is changed. Okay. Changed in the plane. Okay. Due to the change in the plane, the conjugation between the benzene ring and C double bond O, O minus is prohibited. Okay. Therefore, this is more stable. More stable. You can say that in the first case, here more the resonance is there, therefore it should be more stable, right? Here more resonance is possible, therefore you can say it is more stable. Due to the more resonance, it is more stable. Okay. More resonance will not increase the stability. More resonance will not increase the stability. Instead, quality resonance increases the stability. Okay. Quality resonance increases the stability. Okay. Therefore, here this is less acidic, and the second one is more acidic. That is due to ortho effect. Consider an example. Here, consider an example. COOH, CH3, again benzoic acid, COOH, CH3, and again benzoic acid, that is COOH, CH3. The question is, among these three, which is more acidic? Okay, coming to first case, as I said now, A is more acidic because of ortho effect. Coming to B, here CH3 is a positive inductive group, and here this CH3 is positive mesomeric group and also positive inductive group. Mesomeric effect doesn't operate to meta position, therefore this CH3 gives only positive inductive effect. Acidic strength is directly proportional to negative mesomeric effect and negative inductive effect, inversely proportional to positive mesomeric effect and positive inductive effect. So based on this, here both positive inductive effect and positive mesomeric effect is operating. So here positive mesomeric effect and positive inductive effect is operated, and here only positive inductive effect is operated. So we know that here A is more stable because of the ortho effect. Coming to B and C, this positive mesomeric effect and negative mesomeric effect decreases the acidity to the larger extent. Therefore, here we have only one positive inductive group. So compared to C, this is more acidic. Okay, and then comes C. Because of these two effects, that is positive mesomeric effect and positive inductive effect, the acidity decreases to the larger extent. Therefore, the order of acidity is this one. Okay. And one more thing you have to remember, that here hydrogen H, D, T, NH2, F, Cn minus, etc. These are all not bulky groups. At ortho position, if H, D, T, NH2, fluorine and Cn are attached, they are not considered as bulky groups. If any groups other than these attached to the ortho position are considered as bulky groups. Okay. Okay, we will move to next. Usually, mesomeric effect takes the preference over inductive effect. If negative mesomeric effect and negative inductive effect is operated, so in this case, negative mesomeric effect takes the preference. Okay. If positive mesomeric effect and positive inductive effect is operated, the preference should be given to the positive mesomeric effect. Here, there are groups which gives positive mesomeric effect and negative mesomeric effect. So in that case, consider A. Positive mesomeric effect takes the preference over the negative inductive effect in the case of NH2, OH, OCH3, NHC double bond OCH3 and OC double bond OCH3, etc. So in this case, positive mesomeric effect takes the preference over the negative inductive effect. So consider another case, in the case of halogens. Okay, in the case of halogens, what happens? Negative inductive effect takes the preference over the positive mesomeric effect. Okay, in the case of fluorine, chlorine, bromine and iodine. Okay? In the case of halogens, negative inductive effect takes the preference over positive mesomeric effect. Let us move on to applications of mesomeric effect. In that, first application is to compare acidic strength of carboxylic acid. To compare acidic strength of carboxylic acids. Acidic strength is directly proportional to minus M effect and minus I effect, and inversely proportional to plus M effect plus I effect. Okay. Okay, based on this, we will answer few questions. First one is, consider
benzoic acid, at ortho position NO2 group is attached. Okay. Next one is, again consider benzoic acid. At ortho position OCH3 group is attached. OCH3 group is attached. And then consider benzoic acid. So this is first, second and third. Here NO2 shows minus M effect, minus I effect. When the group shows minus M effect and minus I effect, minus M takes the preference over minus I effect. Here OCH3 shows plus M effect, minus I effect. In this case, plus M takes the preference over minus I. Only in the case of halogens, minus I takes the preference over plus M effect. Okay. This is possible only in the case of halogens. So here in third case, it is only a simple benzoic acid. Acidic strength is directly proportional to minus M effect and minus I effect, and inversely proportional to plus M and plus I effect. Since minus M and minus I both are operate on this, so therefore first one is more acidic, and again and plus M decreases the acidic strength. Okay, therefore next is third and next comes second. This is the order of acidity. In the first case, both minus M and minus I can be seen, whereas minus M takes the preference. Acidic strength is directly proportional to minus M, therefore acidity increases. Coming to second case, plus M and minus I effect is absorbed, but plus M takes the preference. Plus M decreases the acidic strength, therefore it is least acidic. Next example. Benzoic acid, at which and at ortho position CH3 group is attached. Next one is, it's a simple benzoic acid, OH. Here at ortho position CH3, and here also CH3. This is A, B and C. The order of acidic strength is, see here one group present at ortho position, and in the third case we have two groups at ortho positions. So here two bulky groups are present at ortho position, therefore ortho effect is more. Here also bulky group present at ortho position, but the ortho effect is more in the case of C. Therefore C is more acidic than A and then B. This is the acidity order.
Next application is to compare acidic strength of phenols. Okay, let's take an example. Take phenol to which NO2 group is attached at ortho position, and again take phenol to which NO2 group is attached at meta position. Again take phenol. Here the NO2 group is attached at para position. So here we know that NO2 group gives minus M effect and minus I effect. Here NO2 is at meta position, therefore it gives only minus I effect. At meta position, mesomeric effect is not operated. Here NO2 is at para position, it gives minus M effect and minus I effect. Okay, when there is both minus M effect and minus I effect, minus M effect takes the preference over minus I effect. Okay, here also minus M takes the preference over minus I effect. We know that acidic strength is directly proportional to minus M and minus I and inversely proportional to plus M and plus I. So here this is A, B and C. Among these three, if you compare A and C, in both the cases minus M effect takes the preference over minus I effect. So coming to first case, here the chance of formation of hydrogen bond is there. Okay, chance of formation of hydrogen bond is there, so that this proton is not easily available. The proton is not easily available. Okay. Therefore, it is less acidic than C. Coming to C, as we said, acidic strength is directly proportional to minus M effect and minus I effect. So, therefore, C is more acidic than A. And then comes B, because B has only minus I effect and minus M effect is not operated on metaposition. This is the acidity order. And we will take one more example, that is phenol OH. Okay. Again, phenol. Here CH3 group is present at para position. Again, we have phenol. NO2 group is at meta position. Again, take phenol. Again, here NO2 group is present at para position. This is 1, 2, 3, 4. Again, the order of acidity. You have to consider order of acidity. So here, this CH3 group gives plus M effect and plus I effect. And here NO2 group gives only minus I effect, not minus M effect, because at meta position mesomeric effect is not operated. Here, since NO2 group is at para position, this gives minus M effect and minus I effect. Here minus M takes the preference over minus I effect. So according to this, we know that acidic strength is directly proportional to minus M effect and minus I effect. So therefore, 4 is more acidic. Okay, 4 is more acidic. Coming to third, here only we have negative inductive effect. That means acidity is directly proportional to negative inductive effect. Therefore, next 3 comes. Okay, therefore the acidity of so in the third case, only minus inductive effect can be seen. So therefore, next acidic strength is 3. And coming to first and second, we know that positive inductive effect on positive mesomeric effect decreases the acidity. Therefore, second one is least acidic. First and then second. This is the acidity order. Next application is to compare basic strength. To compare basic strength. Okay. So that is basic strength is directly proportional to plus M and plus I effect and inversely proportional to minus M and minus I effect. Whereas acidic strength is directly proportional to minus I and minus M effect and inversely proportional to plus I and plus M effect. But basic strength is directly proportional to plus M and plus I effect and inversely proportional to minus I and minus M effect. Next is more the availability of lone pair, more the availability of lone pair on nitrogen, more will be the basic strength. More will be the basic strength. Okay. We will see in gas phase, the order of acidity of nitrogen is CH3 NH2 is, in gas phase, the order of basicity of nitrogen is CH3 NH2 is less basic than CH3 twice NH is less basic than CH3 thrice N. Okay, here in all cases nitrogen will be having lone pair of electrons. Okay, the next one is localized lone pair. Localized lone pair of electrons are more basic than delocalized lone pair. Delocalized lone pair. Okay, we will take example. Here NH2 and here we will be having a benzene ring to which NH2 is attached. In both the cases, nitrogen will be having lone pair of electrons. In the first case, the lone pair of electrons are easily available because they are not involved in any conjugation. That means these lone pairs are localized. Okay. So coming to second case, these lone pair of electrons involve in resonance. Okay, involve in resonance. This lone pair involve in resonance. Therefore, this lone pair of electrons are not easily available. Not easily available when compared to A. Not easily available when compared to A. Okay. Therefore, this is less basic. Next application is SIP. That means steric inhibition. Steric inhibition in protonation. In protonation. Okay, this is SIP. This is seen in primary aromatic compounds. Primary aromatic compounds. Okay, let's take an example. NH2. Okay. Okay. Here H plus. This lone pair of electron attacks H plus. Therefore, what happens? Here NH3 positive charge on nitrogen. Okay. This is more stable. More stable. And consider again benzene ring to which NH2 group is attached. At ortho position, there is a group attached. Okay, there is some group attached. So in the presence of H plus, what happens? Then again the lone pair of electron attack the H plus, giving NH3 plus, and here positive charge NH3 plus, and here at ortho position G is attached. So we know that NH2 F CN HDT. These are all not bulky groups. Not bulky groups. But here, this is NH3 plus. This is bulky group. Okay, bulky group. When the bulky group is attached here, what happens? So here, because of the bulkiness, there is a repulsion between these two groups. Therefore, this is less stable. Less stable. This one is less basic. Less basic. Here, this is more stable and this is more basic. Okay. This is according to steric inhibition in protonation. These are the applications of resonance effect. If you found this video helpful, please do like, share and subscribe. Thank you.